We will continue the problem in lecture 15, right. We have covered various aspects as discussed earlier, the operations of engine, types, ray diagram, kinematic diagram, number of teeth in each gear, gear failures, gear material selection, model calculation, shaft design, lubrication selection. So, these are the things we have covered, and today we are going to discuss about lubrication method, including bearing selection, gearbox losses and gear casing, and finally gearbox mounting aspects. All those the blue color topics we are going to discuss in today's lecture. You can see that the lubrication, right, how is going to be applied in the gearbox. This is the spray type. What you have seen on the left side is a spray type, on the right side is a bath type. Both are different. Bath means the gears should be fully immersed. You can see this is the pinion, which is the one which is fully immersed, such a way that the lubrication is circulated, whereas in the spray system, that only a small amount of lubricant is there, up to maybe covering the base circle of the pinion, right, base circle. From there it will make a contact, and whatever the lubricant remaining, it's coming back with the free gravity, or else you can have a jet. Using the jet you can apply a lubricant where they are going to have a contact. So, the bath lubrication system, this is the simplest system, limited to pitch and velocity when it is approximately 17 meter per second. The gear should dip into the oil bath above twice the tooth depth to provide adequate splash for pinions and bearings to reduce the losses due to churning. And the moment you increase the speed, splash loop system can be extended up to 25 meter per second, but the provided should have a proper cooling system, including breathers, to avoid churning losses. Normally, I am talking about circulation lubrication system. Normally, when the pitch line velocity more than 25 meter per second, when you have a high velocity, right, in that case you can have a circulation lubrication method. For gearboxes with the anti-friction bearing, spraying oil at the gear mesh only and relaying the splash to lubricate the bearings permissible up to a maximum pitch line velocity of 35 meter per second. If the speed is increased above 35 meter per second, then the both gears and bearings should use pressurized feed, which is the feedback system, right, pressurized feedback system, in other words called as a circulation method. If pitch and velocity less than or equal to 40 meter per second, there you need to have a oil jet should be placed on the incoming side of the gearbox, because whenever the gear meshing, right, at the inside you will have a more heat, right, inside you will have more heat. So, you have to focus to reduce that, and you have to focus or you reduce that. And a pitch velocity above 40 meter per second, more oil is needed, more for cooling aspect than the lubrication aspect. Obviously, the contact will be more, the number of contacts will be more as increasing the speed. So, the heat generation would be more. So, you have to give adequate lubricant, instead of not just lubricating purpose, it should remove the heating aspect. So, that is how you do the energy balance. If gears are operating at very high speed above 85 meter per second, the amount of oil is carried to incoming gear meshing not adequate and danger of gear mesh. So, in that case, to avoid this, 2/3 of oil flow outside the gear mesh for cooling aspect, 1/3 alone inside for the lubrication aspect. As you are aware of that, initially in the previous lecture I have told the purpose of lubricant, it is not only to develop a film between the two surfaces, but it also remove the heat. The two purposes, two main purpose for any lubricant. So, as you increasing the speed, the heat generation would be more. You may ask question. So, you take your two palms, rapid slowly, do you feel heat? Won't. Okay. The same thing if you do very faster, what happens? You will feel the heat generation. Why it's happening? Because you are not allowing the time, enough time to heat it, dissipate. Right, that's what happens. So the heat is keep accumulating as moving, as rubbing in a higher velocity. So that obviously would generate more heat. Right. So this is what precisely happening. So at a higher velocity, the 2/3 of oil flow outside gear mesh for cooling aspect, 1/3 of oil flow inside the gear mesh for the lubrication happens. If velocity more than 100 meter per second, circulation must be provided optimum number of and location for jets, as where jet will precisely flow the lubricant. Okay. Yeah. Quantity of lubrication, that is also very critical. So this is standard equation. This is a VL equal to P by C, where P is the power input in horsepower, C equal to constant. Will tell you what does that mean. VL is the amount of lubrication. Okay. For example, we have a gearbox in various applications, starting from machine tool to automobile. Even you can space application also we can be there. Okay. So where do you expect more quantity of oil? Where do you expect more quantity of less quantity of oil? Obviously, in the space application, the lubricant has to be as small as possible. Okay. The next is automobile, then machine tool gearbox. So in fact, if you look at, you can see this is the C, the equation, maybe I will go back. VL equal to power by C. C is the constant, normally per horsepower, okay, gallon per minute is clearly given. So for India, you can see that 200, 400, 800 and 1000. So 200 is P is general, that means adequate lubricant amount, industrial application. The moment the C is increasing, the quantity of lube is decreased. So it is for adequate aviation aspect, and if it's 800, it will be a lean condition, where you need to have a light and high aviation space application. This is again for 1000 as a stopped condition. For your general gearbox, automobile gearbox, right, is falls under this category. Anything on the aviation is falls under 400 or and 800. Right. Now we will move on to the gearbox classes. This is the general equation. Eta is the efficiency, P is the power in, and PL is the power output. You can see again this gear loss, there are so many gear losses are there. You can see the power loss in gear teeth engagement, power loss in bearings, power loss in seals, and power loss due to churning. Okay. When two teeth are contact each other, this is happening through friction, right. So that will create a loss, that is power loss in gear teeth engagement. Second is when you have bearings, again they rotate, right, the bearings are rotate against the friction. So the bearings also constitute friction losses. Then the seals, which is to prevent any leakage in the gearbox, they will also constitute a power loss. These three, I am talking about gear, bearing and seals are related to your load aspect. They are related to load factor. Churning nothing to do with the load, but it is related to the speed. Churning, it's like you are making a speed. Higher the speed, the sharing between the lubricant higher, internal friction will higher. Obviously, the heat generation will be there. The moment you have heat generation, the viscosity reduces. Remember, higher viscosity, low speed, high speed for low viscosity, the same thing, right. The churning also will cause losses. Let me ask question, you have 4 losses, among these 4 losses which would be more? Is it from gears, or is it from bearings or seals or churning, right. Obviously it would from gears, right, because that's the one which is making the contact, right. They are the more the gears, more the power loss. Whereas bearing is limited, so as seals also. Maybe you can see this is the equation, power loss in gear teeth engagement, which is the, you can see this is the equation, you see in that, right. Z1, okay, is the teeth, number of teeth is engaged, and V is the your pitch and velocity, you can see that velocity of gear, which is pitch line velocity. P is the power input, and alpha is the pressure angle, right. This is for single stage, the above equation for single stage. If multiple stage, then each stage should be multiplied with the first stage, so that you will have cumulative power loss. Okay. So, normally the equation, okay, it is a simplified here. Usually we will have a friction coefficient. Usually we will have friction coefficient. Again, the friction coefficient is variable, depends on the your surface roughness, lubrication, flash temperature, and bulk temperature of the material. There are so many factors are there. So, I do not want to give very complex equation. For your understanding, I have given the very simple equation for power loss in gear meshing aspect. Then this is standard equation, power loss in bearings. You can see here TB is the frictional torque, bearing torque, mu is your coefficient of friction, you can see it taken from the SKF catalog. P is the equivalent load. I will tell you what is the mean equal load when we discuss about the bearings aspect. D is the bore diameter, okay, B is the bore diameter. This is for the bearing loss in bearings. Yeah, you can see that. So, this is taken from the SKF catalog, right. There are coefficient of friction is given. If you look at the least coefficient of friction where you would expect, right, the least coefficient of friction probably is your self-firing ball bearing, you can see this is the one. Then next one would be the thrust ball bearing, okay, thrust ball bearing. Then you will have a deep groove ball bearing and spherical ball bearing. So, depends on the application, you have to choose the bearings for your gearbox selection. Yeah, still we are continuing with the power loss in bearings. PB equal 10 power force, another equation. TB is the frictional torque, N is the number of speed in the shaft aspect, that is one more equation. And this is for the churning aspect. Yeah, the churning aspect will come lot of aspect, okay. Your V is the velocity is given, and these two teeths, the one number of teeth of drive and driven respectively Z1 and Z2, and eta is the viscosity of the oil at operating temperature, it should be in centipoise, okay, we have done. Then more importantly we are talking about the phase width, okay. If you have the more surface, right, more surface, that means more surface has to be interact with the lubricant for churning. Churning means nothing but you are keep rotating, okay. You have assuming that you have a box filled with the lubricant, put the gear and keep rotate, right. What happened? If you have your phase width smaller, what happened? Your losses, churning will be smaller. Higher the size, higher the churning loss. So, again that depends on the thickness of your gear. Thickness here it means a phase width, okay. So, you can see here the B is given phase width, C is the factor, normally again depends on the what type of operation you are going to use, whether you are going for use the splash aspect, right, if 0.009 is already taken experimentally, then 0.006 for the spray lubrication aspect. Finally, we will come for a power loss in seals. This you can see that PS equal to TS W, TS is the frictional torque in seal and omega is the angular velocity of the shaft, and from TS, right, depends on mu into Fr into R, where mu equal to seal friction, Fr is the radial lip load, and R is the radius of the shaft. So, standard equation for a frictional torque aspect, right. And if look at this, is I have taken, this is the comparison power loss in the whole gearbox for different speed. Obviously, higher the speed, higher power loss, that you can see the trend. Among them, the large amount of fraction it goes to your gear meshing. You can see that this is gear meshing. The next is churning, okay. Then you will have the bearing aspect, right, the bearing and the seal, and finally there is called synchronizer. So, synchro mesh gear, which is going to have a another loss also, but so far we discussed only for the gearing, churning, bearing and seal. So, you can see, right, more the gears, more the power loss. Yeah. Let me ask question, what is the typical efficiency of the gearbox? Is it 80%, 85%, 90 or 95 or above 95? Usually the standard gearbox efficiency 90 to 95%, already optimized, fully optimized. So, anything if you want to improve the optimization, to increase the efficiency, you can do maximum of 1%, that is a big achievement, okay, that is the big achievement, and people are doing lot of aspects. And now we will move on to the gearbox housing consideration. Remember, the gearbox, it is not only power transmission, it should give the structural support also, right. So, in that aspect we need to find how to place them, that is also very important. You can see. So, the following requirements have to be taken in account when designing the housing: observe the acting operational forces and moments, guarantee the exact position of the shafts and the gear wheels. Gear wheel means gears relative to each other in the various operating states, ensure good heat conduction and radiation, insulating and damping the gearbox noises, easy to fit and remove, and should be rigid layout and should provide good strength characteristics combined with the low weight. You do not want to have very high weight, okay. And this you can see there is a how to mount them, right. So, you can see this is the called through housing, this is called end loaded, okay. Normally we will go for the top loaded housing, this is what preferred one, okay. The reason is, compared to other things, precise production in one clamping operation, very easy to fit, and you can split two offs, you make it, you can see that they are joined through two shafts arrangement, two offs things, okay. So, but this is very expensive though, okay, it is very expensive, that is the only disadvantage. This is the way you have to arrange, which way to want to do that, and you can see this is the typical ZF eco split, which is two off I said, right. It is a commercial vehicle gearing with the loading housing aspect, and the lot of research going on. This is called windage tray, this is called the windage tray, say that, okay. If you look at inside, they will have intricated path will be there, so that it will guide lubricant to flow to the respective ways also, okay. The lot of CFD analysis done to design the windage tray aspect, that is another research level, but this is only for your understanding. We are not focusing above the gearbox casing design aspect. You can see the again housing, the large gearbox housing generally casting made from cast iron or steel. Cast iron is rigid metal with excellent vibration damping properties, and fabricated steel gearbox are used in special cases. Gearbox used for transmission vehicles are often made from cast aluminum for lightweight aspect. Smaller tiny gearbox units are made from variety of materials including cast zinc alloys, okay. And if you look at, very interestingly, when you talk about the gearbox cast, your housing alone will take 36%, the gears are 22%, the shaft is 20% and bearings 10%, the others are 12%. So 35%, one third of the price goes to your housing itself, because that's a complex, that is very complex. It should have a lot of intricate the flow aspects also. This is the mounting aspect, foot mounted below horizontal force and flange mounted on the prime mover, shaft mounted with the torque arm to prevent the rotation of gearbox, right. And you can do the same foot mounted on the vertical surface. You can see this floor mounted gearbox, top mounted gearbox, shaft mounted sideways gearbox. Okay, this is the through shaft arrangement mounted gearbox, and this is gearbox flange mounted on motor aspect. Tell me which one is the easier, most preferred one? Floor mounted gearbox, right? The floor mounted is the much easier. Okay, whereas this is carrying the additional loads. You can see that the top mounted one, and this also, this is the problem. It's vertically you are loading the gearbox, that is not advisable. So similar way the shaft mounted also is the most preferred. Either go for a floor mounted or gearbox flange mounted on the motor aspect. Have you seen how the gearbox is mounted in the automobile gearbox? Okay, maybe we will see it when you go for the transport lab. At the time you will understand what, maybe if you get a chance, have a look, right. And maybe I will go back here. So assuming you taken the floor mounted gearbox, so which part of the side the gearbox should be thicker, other parts will be thinner? Can you guess? The one which making to the floor contact, right? The bottom, that should be more thicker, because that's the one is holding the entire thing. Whereas the side way at top, you can have a smaller thickness of the casing aspect. You can see that the casing, right. This again non-case hardened gears and case hardened gears, depends on the things. This is taken, this is just guidelines, it can be variable, right. And if look at, if you have a good welded steel welded construction and steel casing, your thickness will be reduced. The above table for lower half thickness of the gearbox, okay, that is what I said, the bottom of the thickness T1, right. And within that, T2 is the wall thickness of the upper half, T3 is the thickness of the mating flanges of the casing, and the thickness of the bottom flange T4. Look at this, what is happening, okay. So this is the standard thickness where it is going to be connected T1, the T2 normally lesser than your T1, and T3 will be thickness of the mating flanges, because that is going to support, you need to have a higher thickness than the lower half thickness. And the bottom flange, remember the entire load is taken, that should be even more higher. You can see the 2 times of your T1. Again depends which way you wanted to mount them, okay. Now we will move on to the bearing selection. Just it is going to give information, because already you would have learned from your undergraduate course the purpose of bearings, okay, to reduce the friction where the shafts, gears or wheels are used, to provide high load tolerance. Application, we have so many applications starting from cars, trucks, heavy trucks, helicopters, aeroplanes, train and so on, okay. What I want to say is, starting from your bicycle to aircraft, you need to have a bearings, right. So the purpose is to make your power transmission smoother with the lesser friction aspect, right. Industries including from milling, mining, oil and gas extraction, production, gear drives, health, positioning control, windmills and food processing, everywhere you have bearings. In fact, I do extensively the wind turbine gearbox failure aspect. It is a Fear-Mitchell failure aspect, where I do extensively research and also I do lot of collaborative work from international companies for a wind turbine. This is the bearing selection chart. So you can see this is taken from Engineering Tribology by John Williams. Depends on the two factors, your load carrying capacity and the rotor's will, based on that what type of bearing you should use it. Okay. So you can have a dry marginally lubricant bearing, fluid flowing bearings, nothing but you are talking about journal bearing. You can say this is JB, fluid film bearings, and rolling element bearing is your normal rolling element bearings, right. The moment you use the medium speed and medium load, you preferred you can have a fluid film bearing. You can see this is the scale, you can see here in this region all are you can go for the rolling element bearings. The moment you go for a higher speed, higher load capacity, there you can go for your journal bearing aspect. You can see that the journal bearing, right. Anything beyond certain speed where you will have a buckling effect, bursting effect, okay, you cannot have it. So you have to choose given based on the load and the speed operation, select the type of bearing, okay, that is general. But in our case we in gearbox usually we prefer to have a rolling element bearings. This is the various comparison between the fluid film bearing, nothing but journal bearing, right, and this is the REB, rolling element bearing. I am just going to compare only these two aspects, right. More importantly, okay, the rolling element bearing starting friction is very less, whereas journal bearing they have to start with the contact. The moment you have contact, your friction is higher. So starting friction is higher for the journal bearing. The moment you start operating, the running friction they are same. The running friction is they are same. You can operate at very high velocity for the journal bearing, whereas rolling will restricted to medium velocity. That is what the chart also shows. And very importantly, you can go for the high load in journal bearing. The rolling element also high load you can do that, whereas the life is infinite life for the rolling journal bearing, because aerodynamic effect, due to aerodynamic effect the shaft is lifted, so there is no contact, so you can use infinite time journal bearing, but that is not possible in rolling element. So rolling element subjected to rolling contact fatigue, RCF, so that is inevitable. That is whereas in journal bearing we can have a finite life. So that is the difference, you can see that. Of course, the lubrication you need to have more for a journal bearing, less for the rolling element bearing. More importantly, I wanted to talk about that is called critical speed, right. They were talking about critical speed where the vibration will come into the picture in journal bearing, whereas that is not needed for your rolling element bearing. Stiffness aspect, I am talking about stiffness aspect. And other thing is the journal bearing will have a high cost, whereas the rolling element bearing is readily available on the shop floor, okay. That is how you can do that. And this is anti-friction bearing, okay. These are again information talking about various aspects. Friction resistance considerably less than in journal bearing. Ball or rollers are rolling contact and sliding friction eliminated and replaced by much lower friction. In plain bearing, when you say plain bearing, it is called about journal bearing. The starting resistance is much larger than the running resistance due to absence of oil film. Already I have explained that. Can support combined radial load and axial load, yeah, which is very important for rolling element, whereas that is not possible in the journal bearing. In ball and rolling bearings, the initial resistance to motion only slightly more than the resistance to continuous running. Shaft alignment can be made with a greater accuracy in the rolling element, whereas that is not possible in the journal bearing, right. Less sensitive to interruption of lubrication. Heavy momentary overload can be carried out without failure in rolling element, that is not possible in the journal bearing. Okay. This is what I said. No self-excited instability, whereas instability or critical speed or whirling speed would happen in the journal bearing. So, the stability is a big problem for journal bearing. Yeah. Okay. This is rolling element classification based on the load. Either you can have a radial load bearings or else thrust bearing for axial loads. Then when you have combined, then you will have a combination. You can see that rolling element bearing classified into ball bearings can be used a high speed operation. The roller bearing can be used for greater load aspects. Okay. Let me ask question. Which one will carry more? If you have a sphere, if you have a cylinder, which will carry more load on the flat surface? Cylinder, because a cylinder is the line configuration, right, whereas the sphere is the point configuration. Okay. So, for same load, point configuration will, right, the load will be very heavy, right, whereas that is distributed, uniformly distributed over the line. That is why the roller bearing, which is our line contact, can withstand more weight compared to your ball bearings. Okay. That is information, and I have some samples. You can see this. This is actually a deep groove ball bearing. You can see that. Usually this is called inner race or bore diameter. Okay, this is your outer race, right. You can see there is a balls are there inside. There is a passage also. That is why it is a groove, right. The balls are placed uniformly, and again with the caging. The caging is allowed to retain the ball so that it will not move away either direction. So, this is deep groove ball bearing, can be used both radial load and axial loads. You can see that. This is one information. Yeah, maybe I will share later. And this is another information. You can see that. Can you see this is a roller bearing, cylindrical, right. So, this is again you have a outer race, there should be inner race, and they are placed nice cage aspect. You can see that this is your cylindrical bearings for higher load application. Again, very interestingly, this is double row ball bearing. This is double row because of there are two rows. You can see that, and also this is self aligning. Whatever the shaft alignment, right? If the shaft is straight is fine, if not little bit inclination, misalignment, still this bearing can able to take the misalignment aspects. So, that is why it is called self aligning ball bearing. So, in fact, there are so many types are available, but I have only 3 bearings. Later stage I can show other type also, right. You can see that you can rotate. So, that is by giving that that kind of flexibility, if you have 2 shafts, they are not collinear, the misalignment can be taken out. So, that is the purpose. Not only that, it can withstand both radial as well as axial load. Yeah, this is self aligning ball double row ball bearing. You can see that there is a nomenclature. This is your width, right. As I said, you can see that, and this is your outer ring, and this is your inner ring, and these things called shoulder. Yeah, this thing you can see that this is called shoulder and the corner radius. Yeah, inner ring ball race. You can see this is the deep groove. You can see that there is a, can see like a groove kind of arrangement. Same thing here is also there, but yeah, when I pass it through, you can look at it, and you have separator or retainer cage. This is called retainer cage, so that I will keep it aligned along when rotators. Let me ask one common question. When the bearings used in the application, would you expect both inner race and outer race rotate, or any given time one race should be rotated? One. Depends on the application. Either you want to use it inner race or outer race. Depends on one. Okay. Depends on the application. You have at any given time only one race will be rotated. Again, this is again you can see that deep groove, filling notch, angular contact to take the misalignment, shielded, sealed, and external self aligning, which is what we have seen it, and double row, okay, self aligning double row also you can see that, thrust bearing, mostly thrust bearing for axial loads, and self aligning thrust bearing again for the axial loads plus radial loads. These are the type of roller bearings. You can see the cylindrical, this is the tapered, look at the shape, very tapering position, again tapered but thrust aspect, and this is the needle bearing. See, when the radial load is limited, for me space is limited, then I can have a very thin bearings, which is called needle bearing. Again you can see this angular cylindrical bearing, and this is the spherical bearings. You can see that so many things. Yeah. So again, for low and medium, you can go for a ball bearings. If you want a heavy speed, heavy loads, large shaft diameter, then you can go cylindrical and tapered bearings. Misalignment between the axis of shaft, then you can go for self aligning and spherical roll ball bearing. For low and medium axial loads, axial load and thrust bearing. Okay, already I was explained these things. For heavy axial loads, cylindrical roller thrust bearing can be used. For combined axial and radial loads, you can go for a deep groove, angular contact, and spherical roller bearings. For high speed application, deep groove, angular, cylindrical bearings are suitable. Okay. So always you have to look at the rigidity also. Rigidity controls the selection of bearings in certain application like machine tool spindles. Double row cylindrical roller bearings or taper roller bearings are used under these conditions. For household application, you can't have a very nice high noise. So the noise become criteria for selection of bearings. Usually you can use deep groove ball bearings for household application. These are a chart for understanding about various aspects: radial load, axial load, combined load, high speed, high accuracy, noise, and rigidity aspect. Similarly, you can see for other bearings also with the angular misalignment, ring separability, use fixed, or all this aspect. Okay, so these are self-explanatory. I'll just skip. Okay, yeah, this is a question of friction. Depends on the application, what type of your bearing are you going to use it, because this is the very important for your bearing loss, you have to use it, right. Yeah, more importantly bearing code. Okay, you will have a code of bearing type, code for the cross section, and code for the bore size. For look at this, number 1 for self aligning, 2 spherical roll bearing, 3 for tapered roll bearing, 5 thrust ball bearing, 6 for the deep groove ball bearing, 7 single row, 8 cylindrical, N is the special type line cylindrical, T is the metric tapered. Depends on the numbers, you have to do that. You can see here, when a 6 is there, 4 digit, the last digit should be multiplied with the 5. If you multiply with the 5, 6 into 5, 30, that is your bore diameter. Okay, that is the bore diameter. Then the in between digit will talk about the diameter series. Then 6 indicate about the type of the bearing, deep groove ball bearing. Similarly, if you look at 7305, 5 into 5, 25, that should be the bore diameter. This is for diameter series, and 7 is the deep groove ball bearing. That's another thing. Now you have a special series, 4 digits. Sorry, this is the 5 digits. 0 9, 9 into 5, 45 is the bore diameter. 2 is the diameter series, and 0 is the width series, and 3 for the tapered roller bearing. NU 2314, 14 into 5, 70 mm is the bore diameter. Then we have a diameter series and width series, and this is for the lips. This is called lips. This portion is called lips. That's the lips aspect. N is the cylindrical roller bearings aspect. This is very important. This is for load carrying capacity. Load carrying capacity, the static load carrying capacity of bearing defined as the static load which corresponds to a total permanent deformation of balls and races at the most heavily stressed point of contact should be equal to 0.001 of the ball diameter. This is the standard equation. Mainly I will go for the important equation is the your load carrying capacity L10. That is the one we talk about the life of the bearing, L10 life. Okay. It is defined assuming that you have 100 bearings. The 100 bearing go for the fatigue test, right. So, they go for fatigue test for 1 million cycles, right. In that 90% of the percentage of bearings should not show any evidence of the pitting aspect. That means only 10% can fail. That is the reason called L10 life. The dynamic load carrying capacity of bearing is defined as the radial load in radial bearings or thrust load in thrust bearing that can be carried for a minimum life of 1 million cycles without showing any evidence of pitting, right. So, L10 equal to your rated bearing life in million revolution, C is the dynamic load carrying capacity, P is the equivalent load dynamic load. When I say equivalent load, because of bearing subjected to two loads, right, axial load and radial load, and 3 for ball bearing, 10/3 for roller bearing. Now you know that this is your point contact, right. So, obviously you can have a certain load, whereas you can go for higher load when you have a line contact. This is what you can see that. For air cut application, the quality of the life bearing is even more stringent. So, they will have called L1 life. That means 99% bearings should complete 1 million cycles without showing evidence of pitting. Yeah. So, again with respect to number of hours, same thing, modify it with respect to number of hours, and this is equivalent load. As I said, Fr is the radial load and Fa is the your thrust load. These are the factors. Again, if your inner race rotates, V equal to 1, if outer race rotates, V equal to 1.2. This is how we have to calculate the equivalent dynamic load. This is the way to how to identify if you have a combined load and axial loads aspect. This is the taken from XY factors from Shigley book, and this is a typical life of the bearings in various application. Automobile costs 50 million cycles, trucks 100, trolley costs 500 million, when railroad cars will be 1000 million cycles. Yeah, you can see that these are various application. Suppose typically a bearing life will be 20 years, supposed to be 20 years. Okay. I am just wanted to point out only two aspects. Instrument apparatus which are only infrequently used for demonstration devices 500 hours, right. The next thing is you can see this 500 to 2000 hours for aircraft engine. What I want to say that aircraft industry is very stringent, the reliability is very important. So, there you can't afford to have bearings to fail. So, they use a very high quality standard. Because of that, there is, though the bearing can able to withstand from 20,000 hours, but you do not want to, but only restricted to 500 to 2000 hours. Similarly, for a precision, the accuracy is very important for a precision aspect, right. So, there also your bearing life is limited, but as you move on to the where reliability is not much consideration, there the number of hours is more. Reliability means catastrophic failures, where is not going to be, where is going to be least, there the bearing life can have a higher number of hours. I think that is the end of the bearing selection. I will stop now. Tomorrow onwards we are going to for a brake system designs. Okay. Thank you.